Sunlight, wind, water, geothermal heat, and plant biomass are all essentially limitless resources. And they're all proven technologies that work right here, right now. The sun provides the Earth with unfathomable amounts of energy. In 1 hour, the Earth receives more energy from the sun than the entire human race uses in a year. With current technology, photovoltaic panels covering 10,000 square miles, or about 10% of the land area of Nevada, could provide all of the electricity used by the United States. Although photovoltaics, converting the sun's light to electricity, was not discovered until the 20th century, solar thermal, harnessing the sun's heat, is an ancient practice. Perhaps the earliest use of solar thermal technology was the south-facing home. Ancient cultures, including the Anasazi Indians of the American Southwest, designed their buildings to face south to maximize heat from the sun, which stays low in the southern sky during winter. In the summer, when the sun is high in the sky, the cliff face that extended over the building provided cooling shade. It's still a common design today.
The Greeks built entire cities laying out the streets so every house could take advantage of sunlight during winter, but avoid it during summer. Now, the Romans went one step further, and they discovered that clear glass will trap solar heat. So they covered the windows with glass. They became what the Romans called heliocamini, which mean solar furnaces.
2 millennia later, the 19th century equivalent of this technology was born, the rooftop solar water heater, which traps the sun's rays in a glass collector and rapidly heats up water inside insulated glass pipes. At the turn of the 20th century, 30% of the homes in Pasadena, California, used solar water heaters. The same concept is used today to cheaply provide hot water to millions, even in cold, cloudy climates.
For almost every homeowner, heating water is the #1 use of natural gas electricity. And using the sun to heat is much cheaper.
Solar thermal energy can also cheaply produce electricity. Giant solar power plants, like this one in California's Mojave Desert, don't use photovoltaic panels to convert light into electricity. Instead, mirrors focus solar rays onto a thin absorber tube that runs along the mirror's focal point. Inside the tube is synthetic oil, which is blasted with intense heat.
Like about 1,000 degrees centigrade. One word of advice, never put your hand at the focus of a concentrating mirror, because it will just make an immediate hole through your flesh.
The superheated oil boils water into steam, which turns turbines. The oil then recirculates through the closed-loop system. In hot, dry areas, solar thermal plants generate serious megawatts at a price lower than typical grid power. In fact, solar thermal plants occupying that same 10% section of Nevada could also supply all of the United States' electrical needs. Meanwhile, photovoltaic technology is surging ahead into its second century. It's come a long way since 1904, when Albert Einstein first proved that light was composed of tiny packets of energy known as photons, which could be converted to electricity. Photovoltaic cells got their first big break in the 1950s, thanks to the space race.
The first 2 Sputniks that went up, they had all this, like, multi-million dollars worth of transistors that went dead in about a week and a half because they were running them on flashlight batteries.
The first artificial Earth satellite in the world has now been created.
The U.S. space program's solar-powered satellites, on the other hand, proved an instant success. Photovoltaic panels still power nearly all satellites and space probes within the solar system. In this sense, the 21st century lifestyle, from global positioning to global communication, is completely dependent on solar energy. The U.S. Coast Guard became one of the first Earth-based users of photovoltaics, powering its remote buoys and weather stations with solar panels wired to batteries. In the 1970s and 80s, solar panels performed heroically during one of the worst droughts to hit Africa. Solar power was used to pump water from 40 feet below the parched ground, saving many lives.
In fact, probably one of the most valuable uses of photovoltaics today is to provide clean drinking water for the developing world.
For those already connected to the power grid, photovoltaics are becoming more and more viable.
A home, say a 2-bedroom suburban American home, gets enough energy on its roof to power itself once or twice over.
And it doesn't actually need to be as sunny as you think for solar to work. The most successful solar program in the world is actually in Germany, and they have less sun in Germany than they do in Seattle.
For the time being, photovoltaic panels are still expensive, making solar electricity 2 to 5 times the cost of typical grid power. But grid-connected homeowners can sell excess peak hour electricity back to the power company at a premium.
The systems do pay for themselves. The payback might be as short as 4 or 5 years. And in general, for residential systems, we're looking at 10 to 12 years. That doesn't take into account some of the other benefits, like, for example, the protection from rising utility rates or also increased property value.
Up until now, the primary cost of solar cells has been the ultra-pure silicon needed for the photovoltaic reaction. But more than one company wants to change that.
The photovoltaics industry is based primarily on wafers of silicon to make high-efficiency solar cells. But those wafers themselves are very expensive. NanoSolar uses thin films of photoactive material instead of those expensive wafers.
Rather than silicon, NanoSolar in Palo Alto, California, uses a combination of semiconducting elements.
So you have copper, indium, gallium, sulfo, selenide. Because that's obviously a mouthful, we get more work done if we just say CIGS, C-I-G-S-S. The beauty of the material absorbs sunlight very readily, so you can make a very thin layer.
So thin that the absorbing material is assembled on the nanoscale, then literally printed onto a foil substrate as a photovoltaic ink.
On this experimental machine, the foil is moving very slowly, but this style of machine can be made to run at tens or even hundreds of meters per minute. And because of this, these relatively inexpensive machines can be used to make an enormous quantity of low-cost photovoltaic cells.
Thin-film solar panels, as well as their silicon counterparts, can be built right into a building surface, such as a roof, window glass, or in the near future, paint. So-called building-integrated photovoltaics will drive down the cost of solar electricity even further.
Because you're not buying panels and the infrastructure, you're buying it all at once. And my lab has been looking at forecasts of getting 20%, 25% of total energy from solar by making it this ubiquitous material that you just get everywhere.